Generative models do not create images out of nothing. They learn to reverse the process of physical decay by navigating the mathematical path from absolute chaos back to structured information. Forward diffusion is a fixed Markov chain that incrementally adds Gaussian noise to an image. This process destroys structural patterns until the data matches a predefined stationary distribution. Each step in the chain uses a Gaussian transition kernel. This ensures that the probability of the state at time t depends only on the state at the previous time step. The amount of noise added at each step is controlled by a variance schedule, often denoted as beta. This schedule ensures the transition to pure noise occurs over a finite sequence. At the end of the forward process, the original image becomes an uncorrelated sample of white noise. All information is lost in this high-entropy, spherical Gaussian state. To generate an image, we must reverse this process. However, calculating the exact reverse transition probability is intractable because it requires knowledge of the entire data distribution. We used a neural network to estimate the reverse transitions. The model learns to predict the noise added at each step, effectively acting as a learned denoising function. The primary architecture for this task is the U-net. It uses symmetrical downsampling and upsampling blocks with skip connections to preserve spatial information across different scales. During training, we minimize the mean squared error between the actual noise added and the noise predicted by the model. This optimizes the evidence lower bound of the data likelihood. The reparametrization trick allows us to sample the marginal distribution at any time step directly. This bypasses the need to iterate through all previous steps during training. Diffusion can be viewed as score-based modeling. Here, the goal is to estimate the score function, which is the gradient of the log probability density of the data. The score function points toward regions of higher data density. By following these gradients, the model iteratively moves samples from low probability noise regions toward high probability image regions. Realistic images occupy a low-dimensional manifold within high-dimensional pixel space. The score function guides the noisy input back onto this manifold, ensuring visual coherence. Sampling is performed using Langevin dynamics. This stochastic process combines the score function with added noise to explore the probability distribution without getting stuck in local minima. Multiple noise levels are used to handle the entire space. Large noise levels help capture the global structure, while low noise levels refine the fine details of the image. Denoising diffusion and score matching are mathematically equivalent under specific conditions. Both frameworks optimize the same underlying objective of reversing a stochastic degradation process. In continuous time, diffusion is described by stochastic differential equations. This allows us to use sophisticated numerical solvers from physics and calculus to improve generation quality. The forward stochastic differential equation defines how a data point evolves into noise. It consists of a drift term, representing the decay, and a diffusion term, representing the noise. The reverse time stochastic differential equation provides the formula for reconstructing the signal. It relies on the score function to counteract the drift and noise of the forward process. For every stochastic differential equation, there exists a corresponding deterministic ordinary differential equation called the probability flow ODE. This allows for noise-free, perfectly reproducible image generation. Deterministic sampling enables the inversion of images back into their initial noise states. This is pivotal for editing specific attributes while keeping the rest of the image consistent. We solve these equations using numerical methods like the Euler-Maruyama integrator. These algorithms discretize the continuous time steps into manageable computations for the hardware. Operating in pixel space is computationally expensive. Latent diffusion models perform the stochastic process in a compressed, lower-dimensional representation of the image data. A variational autoencoder handles the compression. It maps high-resolution pixels into a latent space, where the diffusion model can work more efficiently on the essential features. The encoder transforms pixels into a distribution in latent space. This step removes redundant information while capturing the underlying semantic meaning of the visual content. The diffusion process occurs entirely within this latent bottleneck. Because the latent space is smaller, the model can afford more complex attention mechanisms and faster sampling iterations. The decoder takes the final denoised latent representation and reconstructs the full-resolution image. It restores the textures and fine details that were set aside during the diffusion stage. To guide the generation with text, we use conditioning. This involves injecting external information into the denoising process to bias the probability towards specific outcomes. Cross-attention layers allow the model to compare image features with text features. The model learns which visual components correspond to specific words in the prompt. The attention mechanism uses query, key, and value matrices. This mathematical operation calculates a weighted sum of information, prioritizing parts of the prompt that are most relevant. Contrastive language image pre-training, or CLIP, provides the bridge between vision and language. It projects both text and images into a shared embedding space where they can be compared directly. Classifier-free guidance improves prompt adherence. The model generates one estimate based on the prompt and another without it, then extrapolates away from the unconditional estimate. The guidance scale determines how strongly the model follows the prompt. A higher scale increases realism and alignment, but can reduce the diversity of the generated images. Denoising diffusion implicit models, or DDIM, allow for faster sampling by skipping steps. This non-Markovian approach produces high-quality results in a fraction of the time. Advanced samplers reduce the number of required iterations from 1,000 to as few as 20. This optimization is essential for real-time interactive generation applications. Cascaded models use a pipeline of diffusion steps. A low-resolution base model creates the initial structure, followed by super-resolution models that add high-frequency details. Super-resolution is also a stochastic process. The model predicts the missing pixels by sampling from the distribution of possible high-resolution images that are consistent with the low-resolution input. The quality of the output depends on the training data distribution. The model can only generate what it has seen on the manifold of its training set, which defines its visual vocabulary. Important sampling is used during training to focus the model on the most difficult noise levels. This ensures that the model learns to handle both the large-scale structure and the fine details equally well. While Gaussian noise is standard, some researchers explore other noise distributions. Adjusting the underlying stochastic process can lead to better handling of specific types of data, such as discrete text or audio. ControlNet allows for additional conditioning based on spatial structures like edges or depth maps. It locks the denoising process to a specific geometry while allowing the model to fill in colors and textures. Low-rank adaptation, or LoRa, enables efficient fine-tuning. Instead of retraining the entire model, we inject small weight matrices that modify the model's behavior to learn new styles or characters with minimal data. The math of LoRa relies on matrix decomposition. By representing weight changes as the product of two small matrices, we drastically reduce the number of parameters that need to be stored and updated. Diffusion models have excellent convergence properties. Unlike generative adversarial networks, they do not suffer from mode collapse, meaning they can represent the full diversity of the training data distribution. The future of image generation lies in more sophisticated stochastic differential equations and faster latent spaces. We are moving toward a world where the boundary between mathematical noise and human creativity becomes indistinguishable. In conclusion, artificial intelligence art is the result of rigorous probability theory and stochastic calculus. By mastering the mathematics of noise, we have unlocked the ability to reconstruct any possible reality from the void of entropy.